Okay, this is, I think, let me check. Yeah, triple integrals. We have learned the change of uh, order of integration. Okay. Now, before we start, anyone does have any? Do you guys have any comments or feedbacks regarding the quiz, the last quiz we have, the quiz on chapter 12 and 13? Do you have any feedbacks? Do you think the questions um, difficult, or do you think the time is not enough? What do you think? Do you think it's difficult? Oh, really? But it's supposed to be open notes, and you can like not sure how you're doing it, but you can prepare calculators, notes, everything you can prepare. So for every quiz that we will have in because for online platform, I believe open notes will be just fair choices, because if I make it okay, closed book, blah blah blah, I don't think that it will be clearly possible. So make it into I just make it open notes. And did any of oh, okay. Probably need to maybe a little bit more time for the true false questions. Maybe 1 minute or 2 minutes, right? 1 minute or 2 minutes. I set some of the time set is around 30 to 40 seconds, right? So I think should be one to or at least 2 minutes, right, for true false questions. Okay. So what my plan is, yeah, yeah, for reading the questions. My plan is actually for the quiz, we'll be using the same platform, the quizzes. Before final exam, I'm planning to use a different platform. Uh, and I think it will be suitable because it's not really having time limit for each question, but maybe time limit for, like, if I make it into several page, so each page will have time, but you can arrange your own time, like manage which one you are going to solve first. So that is my plan. And yeah, for the online final exam, probably we are using the same as WebEx, and then I will set uh, the final online platform, and I will send the link later on. Okay, we will use the different platform, so not using the quizzes. Okay? Quizzes is just for, I think, just for a quiz. Okay, I think I get some feedback from you. All right, now let me just review a little bit. Okay, what we have here. So basically, uh, for the change of order integration in triple integrals, the basic idea or the essential things that you need to make a concern with is to make a projections. Okay, so if you have this three dimensions, you already have this three-dimension shape. What you can do is imagine this as a 3D projection. Okay? And then from here you can have this three projection through the xy plane, yz plane, and the xz plane. Okay? And now from here we could write some intervals and their alternatives. Okay? So this is the intervals, the first one. and their alternative is the second one. Okay. Okay. So I believe sketching the curve is essential. Okay, now the next section is about the applications of triple integral. Okay, recall in calculus 1, if you have a function that is positive, then this integral represents area under curve from A to B, right? And for the uh, function of two variables, if it is positive, then this will be represents the volume under surface C and above the region D. Okay. But how about the triple integral? Now this will be a very difficult to imagine. But right here, this should be hyper. Let's say hyper volume. But of course, it's difficult to visualize. So when you have from one from two dimensions becomes three dimension, and from three dimension is supposed to be become into the fourth dimensions. And um, if you learn a little bit of physics and maybe watching some science fiction movies, or probably watching some documentary series about physics, um, if you would like to imagine a fourth dimension, it's supposed to be, because fourth dimension is time, right? Time, and from one dimension to three dimension is a space. It's supposed to be the phenomenon is supposed to be you have a space that moves, and it moves during some period of time. So it could have some. So if you would like to draw the visuals, it's like a movement. It's having some movements, and I think it's very difficult to visualize in terms of, if you want to sketch it out, it will be very difficult, right? Difficult to visualize. So it's not very useful if you would like to sketch this triple integral. But let's say we would like to interpret this. Um, let's say if the functions is a constant, let's say just one, okay, for all points in E, and we can say that if this happen, then we could interpret this as a volume of E is triple integral of dv. Okay, and this becomes one aspect to apply triple integral to calculate the volume. Okay. So if you would like to construct this, we construct from the beginning. Okay, let's say we concern on the surface. Let's say we have the surface U1 and U2, the upper and lower surface, and this is supposed to be dz, and the rest is the double integral will be just dA, and this was supposed to be d, and this will be u2xy minus u1xy, right? And this is supposed to be dA. And if you look here, this is precisely the volume that lies between two surfaces, right? Between surface z equal u1 and z equal u2. Okay, so basically what this implies is we could find the volume from the interval of E. Maybe we can try some examples, but let me just give you a few minutes to wrap up and take maybe some notes from here. Okay, I think we can move to the next question. Okay, move to the next questions, for example. Find volume of tetrahedron T bounded by planes x plus 2y plus c equal 2, x equal 2y, x equals 0, and z equals 0. Okay. We have two planes. Okay. So what we can do first, and I think this planes and this line here, I think not too difficult to draw, so we can draw first. I think we can draw and find the intercept of each axis. Let me try to find, is there any, okay, wait. Okay, I think this is, if we could draw. So first finding the intercept, which is 2, this is 2, this is intercept actually up until here, this is also 2. But since we have uh, x equal 2y, so it should be crossing this, and our plane supposed to be go here. Okay, so that is supposed to be our plane, but since we cut this with the x equal 2y, then we have a line here, and thus this is the the tetrahedron T. Okay. Okay. So this line, the x equal to y, is creating a plane here, right? So all the lines interject each other and producing this tetrahedron. Okay. Now, from this intersections, if we project through the xy plane, this is what we have. Okay. This is the line. It's x equal to y. We could write as y equal x over 2, and this one this one is line for x plus 2y plus z equal 2, but z is equal 0, so x plus 2y is equal 2. Okay, and we could find the point. We could check through some equaling this two. So we could say 2y plus 2y equal 2, or 4y equal 2. So y is half and x is 1, right? And to find the volume, we could start to write that is the first steps. Second steps, we could uh, plug in all the essentials, and because we are going to um, have uh, this plane, we say that this is our upper surface, and our lower surface is just the xy plane, right? Or we could say, if you would like to write in terms of z, is 2 minus x minus 2y, and the xy plane is z equals 0. So we could write that as our first integration here. So this will be for dz. And second, we could start dy dx or dx dy. But let's say we just keep dy dx, okay? Because I believe both will be okay if you would like to write in terms of the interval. So x will start from 0 to 1. So this is 0, 1. And y will start from this point here, right? And this point, right? So we could write this one is x over 2, and this one is 1 minus x over 2. So this is dy dx. Alright? Okay, next, we could just solve the equations. So we could have 2 minus x minus 2y dy dx. And I believe you could finish this off, right? So you could have 2y minus xy minus y squared, and we could write y 2 minus x, and start to put in all the information. So we could have 1 minus x over 2, 1 minus x over 2, 2 minus x minus 1 minus x over 2 squared minus x over 2 squared, right? And you can check the solutions. It's supposed to be equal to 1 over 3. Okay. And other application is actually related to the to the density and center of mass, but I think because we skip it the entire section, so we just skip that applications. So again, 15.4, we skip that point, skip that section. Okay, probably a little bit more example on these applications if we have. Let me check if we have more. Uh, okay, let me check. Um, okay, let me go through another example. Another example. Okay, evaluate. Okay, we have this surface. Okay, probably I could give a few minutes for you to at least try. Okay, let's try, and maybe you could also uh, learn to draw, familiar with the drawings. If you find the answer, you can write the answer in the chat box. Okay, anyone get the answer? Anyone with the answer? By the way, probably around next week. I think I will give you last quiz, chapter 14. Please make sure you check out the Moodle. Okay, now we could start with uh, write all the interval of E. Okay, we could write the interval of E. Uh, I believe we need to set up. I think we could just draw like a picture first to make it more clear. Okay. Now first we could start with uh, 1 minus x squared. So minus x squared is supposed to be here, right? When you move out, plus 1 goes upwards, maybe around here. This will be your, make it more beautiful. Okay, maybe that is the graph. Okay. And when we make this curve into 3 dimensions, we would have a plane, right? We will have a plane. We will have a surface. So maybe around here. Go again. Oh, it's supposed to be y equal to, sorry. Maybe let's imagine this is 1. Maybe 1 is here. 2 is here. So it's supposed to be up until here. And x squared minus 1 supposed to be goes over there, right? But it should be minus 1 goes down 1 unit. So it goes down. Okay. And goes down. And having connection line go to there. Connection line between here. Okay, I think we get the at least the shape, right? Okay, we could find the intersections through just some equaling this surface. So this will be plus minus 1 for x. So x is start from minus 1 to 1. We could say this is minus 1. Sorry, plus 1. This is the minus 1. Right. Okay, I think we can start to write the interval. So E x is minus 1 to 1. Y is from 0 to 2. And z is from x squared minus 1 to 1 minus x squared. And I think that we just write all this information into our triple integral. I think not very difficult to to calculate. I think we can just, easily calculate this. 1 minus x squared minus x squared minus 1. So minus 2x squared, 1 plus 2 minus 2x squared. Right? And then multiply with x minus y. So we could get 2x minus 2x cubed minus 2y minus plus 2x squared y. And I believe this is supposed to be 6 over 6. What do you mean by that? Oh, final exam? Oh, yeah, probably, yeah, at least before 10 of June. Let me check. I think we have a schedule. Supposedly we have a schedule on, yeah, probably 6. Probably 6. 6th of June, probably. Morning, Monday morning. And yeah, I think 6th of June would be best. Yeah, we'll let you know the decisions, right? Yeah, but I think 6 is okay. And I think this part you can calculate easily, right? You can find easily. Supposed to be equal with minus 16 over 3. Okay. Okay. Yeah, 12 to 15. Yeah, supposed to cover 12 to 15, but majority will be 14 and 15. But 12 and 13 will be not really that much. Focusing on the 14 and 15. Okay, I think we can move on. Uh, this is just an example. You could try another examples as I later on attach in the Moodle for the PDF file. And I also uploaded the video on exercise chapter 15. But I haven't announced, but maybe later I will announce in the Moodle also. I've uploaded new video about some exercise in chapter 15. Okay, move on to the next chapter, not next chapter, next section on chapter 15, which is 15.7. Okay, the title is Triple Integrals in Cylindrical Coordinates. Okay, so triple integrals, we already discussed what is it, what is that, and how do we apply our knowledge to find the volume in triple integrals. We already discussed, just recently discussed, and now we have the cylindrical coordinates. First, we need to know what is the cylindrical coordinates. Okay, so basically, if we know that we can convert some rectangular to a polar, which means that we could say that through some conversions, we could convert x, y into r, theta coordinates, right? And basically, what cylindrical coordinates is, actually, it has a polar component. And let me just write very quick what we have in the conversions. Okay, through some conversion, we can convert from xy to r theta, right? And basically, what cylindrical coordinate is, we have the polar, okay, we have the polar r theta, and we have another axis which we call z. Okay, so if, for example, I write 2 pi over 3 and 1, which means this is having radius theta and 1 is c. C is the height. Okay. So if you could imagine, and you could possibly moving this point P, you can move anywhere here. You could say that it will change its angle, it will change its radius probably, and it will change its height. Okay, and that's how we define the positions in cylindrical coordinates. Okay. Now, if we would like to observe what it's how the cylindrical behave, okay, this is 3 possible route for cylindrical. So of course, the first one is supposed to be a cylinder because it's cylindrical. So if you have a radius as a constant, like you have the x squared plus y squared equal 4, like in the chapter 12 we learned about this, I think, or in the chapter 13 when we learn about the vector in space. We learned that if we have this is a circle in 2 dimensions, but when we apply in the 3 dimensions, it became a cylinder, right? And it can be described as this picture here. Okay, now if you have the angle, okay, now the angle is a constant, so it's not going anywhere. It's not rotate anywhere, so it's just stay as it is. It stay as it is. So you could say that it has a vertical plane on those constant angle, right? And if you have z as a constant, then it's supposed to be you can go in any point here along the plane, but of course you can go you cannot change the height, right? So it's supposed to be just horizontal plane. Okay? We could say that this three possible shape for the cylindrical coordinates. Okay, now after we learn the geometrical perspective on the cylindrical coordinates and how do we apply cylindrical coordinates, next is how do we correlate with the triple integrals. Okay? So basically, because we have learned the double integral in polar, to apply in cylindrical coordinates, it's not very different. Okay, it's pretty much the same when we apply with the polar coordinates in the double integral. Okay? So first is put the drawing. Okay, it's supposed to be this one. Okay, the first thing we can do is, of course, we are going to look at this surface, these two surfaces, upper surface and lower surface, and we could see that the surface is a function of two variables, right? So it's supposed to be, so if you have like the previous one, you have D, and then this will be the surface, right? And if this is the f, x, y, z, this is supposed to be the z, and the rest is just the a. Now the idea, okay, I think we already also discussed in a few examples, right? So we deal with the dz first, and then later for the dA, we could convert into polar if you see any polar situations in our functions, right? So similarly, what we have here is we could write first. We could write, let's say this is E, okay, the solid E is basically, so xy is element D, and u1 xy is the surface, so z less z less u2 xy, and d will be, we define d in terms of polar r and theta, and let's say we have from alpha and beta, and the radius defined as a function of theta, as a polar curve, right? As a polar curve. So we could have, okay. And now the equations, the triple integrals becomes, let me write here, this is alpha beta, the polar, this is the radius, and this will be the surface, and this will be f, and we convert all into polar. And still don't forget to add additional r, and then dz, dr, d theta. Okay, that's the triple integral in cylindrical coordinates. Another way that you might see how does this make sense, if you cut out the small elements from the cylindrical coordinates here. So we cut the small elements. You could imagine like a cylinder, and you cut out some part of it. So you cut out this part. So you cut out, and comes this, right? And all the volume, all the d, we could multiply as a volume of rectangle. So we could say that dz multiply with the r theta dr, or we could arrange into more clear arrangements. Okay, so the order should be very important. So the the last double integral should be in polar, so this should be the polar, and this one should be a surface. Okay, surface, upper surface and lower surface, and it can be in xy plane, in yz plane, xz plane, depends on the situation. Okay, we could have some example. Right? We could have some example. Okay, and we'll wait for a while. I'll let you take some screenshot if you want or take notes. Okay, now let's say we are having an example. Okay, evaluate triple integral e x squared dv. E is the solid that lies under paraboloid z equal 4 minus x squared minus y squared and above xy plane. Okay, so first is we need to focusing our object to the z here. Let me just give you a few minutes to do some observations and making a sketch throughout this paraboloid. Okay, so just for some thought, okay, for discussions, every time you have a triple integral, you have some function inside. If you want to draw all the things here, it is not possible. It's impossible to draw. What we are going to draw most of the time is this part and its projections. Okay, we can draw this, we can draw E and its projections, but the whole thing as visuals, it's impossible to draw. Okay, now let's say we have this paraboloid. I think this paraboloid is uh, because z is the main axis, so it's just like that, and having this circle here. Right, and let me just draw and insert the picture. Okay, so this is our paraboloid. Okay, and because it's the boundary is on the xy plane, which is the z equals 0, so you could say that the intersection is supposed to be 0, 4 minus x squared minus y squared. So x squared plus y squared is equal 4. So a circle with a radius 2. So we could say this radius is 2 for the circle. And I think we could just do this triple integral in the cylindrical coordinate. We can put on the equations. So we could write down e x squared dv let's say dy dx like that, Or maybe just directly write the polar. We change let me write different color. X squared become R cos theta squared R dz dr d theta. And this will be 0 to 2 pi, 0 to 2, and z is from 0 to, we can write this as 4 minus r squared, right? So we could write here 4 minus r squared. Okay. Now we could start writing this is 4 minus r squared. And this will be r cubed cosine squared theta dr d theta. Okay, I think we could write this as cos squared theta d theta, and this will be 0 to 4r cubed minus r5 dr. Yeah, we could do that. This is a special property in double integral or multiple integrals, right? When we have different, we could see a group of functions, then we could separate those functions into a different variable. And we could solve this, and this will be 1 plus cos 2 theta over 2, right? So we can have half, and then a theta plus sine 2 theta over 2 from 0 to 2 pi. And this part will be r with power of 4, 6602. This will be pi, right? This will be pi, and this will be 16 minus 64 over 6 or 32 over 3. So 48 over 3 supposed to be 16, right? 16 over 3 pi. Okay, perhaps any questions? I believe not too difficult, right? For cylindrical. So basically, it requires you to convert through polar system and then make it into adding one more variable as its height. In our case, this belongs to dz, right? And sometimes the question is probably asking, let me just write here. You are given the triple integral, and then what you can do next is you could choose which way you are going to solve this. Okay, that's the question. Okay, maybe I'll wait for a while if you want to take notes from the previous example. If you have any questions, you can let me know. Okay. Okay, I think we can move on to this example. Okay, so perhaps from what we can see is obviously a polar situation, right? We could say um, we try to develop the solid first, to develop the interval of each axis. Okay, now from here, I think it's obvious for obvious reason. We could see that x squared plus y squared is supposed to be 4 from base um, interval, right? And x squared plus y and z is from x squared plus y squared until z equal 2, right? Now, I think we can imagine. We see that we have x squared plus y squared equal 4 from, if we could draw, let me check if I have the drawing. Oh, I have it, right. Okay, so we could see that the projection is precisely equal to this circle, right? Precisely equal. And we could see that this is having radius 0 from 0 to 2, and its angle will be just a full circle 2 pi. So we could write the equations, becomes triple integral. Okay. So this is supposed to be 0 to 2 pi, 0 to 2, and z will be this x squared plus y squared until 2, right? So we could write as, and this is supposed to be just r, right? R and 2. And inside is just x squared plus y squared, which is the r squared. Multiply with r will be r cubed, dz, dr, d theta. And this we can simplify. So dz becomes z, so it's become 2 minus r cubed, dr, d theta. And I think it's not too difficult to finish off, right? You could say it's going to be having 2 pi, and this will be 2r cubed. So r4 from 0 to 2, this is 2 pi 16 minus 32 over 5. Okay, so it's supposed to be oh, it should be 2, right? Should be 8. Sorry, should be 8. So 40 minus 32 is 8, so it's 16. 16 over 5 pi. Okay. Okay, I think it's not too difficult, right? So 15.7 is supposed to be not difficult. That is precisely depends on your knowledge on the polar system and also the double integral on polars. We have discuss it. It for obvious reason, it depends on that sections. The next section is another way we could do on 3 dimensions. So we could have, first is the cylindrical coordinates. The second one that we could convert the triple integrals could become a sphere, okay, spherical coordinates. So we could take the 3 dimensions, the rectangular space, into another system that we call the sphere. Okay, let me wait for a while for you to take notes or take a screenshot. Okay, we could go to the next section, hopefully. If we have sometimes later on in the future, before the final, I would like to just take some notes and review to give you some self preparations. Okay, or if we don't have time, maybe just take some additional videos and upload for you. Okay, in the future for another practical exercise. All right, now move on to the next section. This is 15.8. This is triple integrals in spherical coordinates. Okay, first is similar to what we have in cylindrical coordinates. First, we need to define what is our spherical coordinates. Spherical coordinates, if you could imagine like a sphere, like a ball, let's say. Okay, now we have the sphere like this, and if we could take a point inside and we define our positions. Okay, there are several ways that we could do, and if we break down this into a system, then this becomes these positions. Okay, so to define this point P, and if we could move this P probably here, here. If we move all this point here, we could see that we could change first is the radius. We could change the radius. So the ball becomes small, becomes bigger, depends on the radius, right? And also the point can be moved through rotations in this xy. So we call this a theta. And also we could have the another rotations on this side. Right? So we could have this and this rotations, right? And we could take into that the distance OP is supposed to be the radius, and since it's a distance, it's supposed to be a positive. So rho couldn't be negative, right, in the system. So it should be greater than 0, and the psi will be in between 0 and pi. Okay, and if you could have some observations, if we could take some constants into one of these variables, we could let me check. Yeah, this this possibility. So we could have, if the radius is constant, it will be a sphere, okay, of course, like we have in the ellipsoid, okay, in the quadratic surface, we have the x squared plus y squared plus z squared. Okay, let's say that's our case. So the radius will be a square root of 6, right? Okay, just to give you an idea. And if you have the constant for the angle, of course it should be a plane, a vertical plane like that. And if you have a half cone, okay, this is if you take the constant from 0 to pi over 2. Okay, so you have some angle here, okay, and you can take it into a cone. And you could have also another way for from pi over 2 to pi. So you could have from here. So you could have another cone there. Okay. Okay, that's the spherical coordinates. Okay, please wait a moment. Okay, I think we can continue on. Okay, if we could describe, okay, how to describe these coordinates, and how to convert. Okay, how to convert. First, we could convert through this picture here. Okay, and then we could say from these two triangles, and these triangles. So let's say we have the triangle OPQ. Okay, we could have the Z. Okay, let's say this is Z. Z here, right? Let's describe Z in terms of the angle phi. So we can have Z is equal the rho cosine the sine, right? And from the triangle OP P prime, we could have the R is rho sine sine. Okay. Okay, now from this xy in the xy plane, we have the similar polar like usual. We could have the r cosine theta, and y is r sine theta. and x is, we could substitute rho sine psi through this r. Okay, and of course we could also write down the whole formulation for the sphere, like as usual, is equal to rho squared. Okay. Now these are all the essentials for the spherical coordinates. So whenever you find any spherical, we could take this into our conversions, okay? And then we could convert and using the integrations. Okay, next is how to integrate basically, and how to make out um, the formulations for the spherical. Okay, it takes time for to make it out for the uh, the spherical. So we could start with we could maybe just take the next sections. Let me go to the next slide and giving you the let me start with this. Let's start with this. Okay, and start with the system of sphere. Start with the I think we can start with A to B. Let's say A to B is our radius. A radius B. I think we could make a little bit smaller this one. Smaller. And then psi, we could say psi is from, let's say C. Okay. That's psi, and then D. Okay. And let A is positive, and beta minus alpha is less equal to pi, and the D minus C is less equal pi for limitation. Okay, so we define the sphere into a small pieces with a delta. Its sides, the delta rho, the delta theta, and this is, it's supposed to be r delta theta, and r is rho sine psi, right? And this side is rho delta psi here. So we already have all this volume. Okay. And if we could add more sides views to make it more clear what is happening here. So from the sides, the pink color, okay. So the pink color, we have delta rho here. This is the rho delta psi. This is from the arc length, right? The radius and the angle, right? and the top view we have, this is theta, this is theta, this is r, and this is also the arc for r delta theta. Okay, and for r, for all r, we could exchange to its to another form, rho sign, and this is also rho sign. And yeah, I think that's all the terms that we need, okay, for conversions. And then from here we could imagine to make it the delta phi. This will be equal to we could multiply all these sides, okay, all the sides from this. It's supposed to be looking like similar with the rectangle, right? So we could have the delta rho and rho I delta psi, and then rho I sine psi k, and then delta theta. Okay, from here you could see that we have a rho squared from this from this rho, sorry, and then rho I squared, and then we have sine psi k, and we have delta theta and delta psi. Oh, delta rho, sorry. Forget delta rho should be in the front. So this will be multiplication of this, and this. Okay. So we have the approach for the delta volume is this. Okay, next is to put into our integral formulation. And we can take some notes that this rho I and theta j and psi k, let's say some point in E. And let the xi, let's say xijk, yijk, and zijk, let this becomes a okay, we could take the triple Riemann sum. Okay, and for fx, and then let's say delta phi ijk. Okay, now we could write down the limit. Lmn going to be infinity. Sorry, it should be Lm. And it's supposed to be rho I sine psi k cosine theta. Theta j, this is k, and then rho I sine psi k sine theta j, and z is rho I cosine psi. Okay, still need to write the delta p. I need to put this a little bit right here. This will be rho. We write the thing here. We put into our equations rho I squared sine psi k delta rho delta theta delta psi. Okay, now we can write, because this is precisely the integral formulations. Then we can write that this is E f x y z dv equal, this is C d alpha beta a b f rho sine psi cosine theta rho sine psi sine theta rho cos psi rho squared sine psi d rho d theta d psi, where E is rho theta psi okay. Okay, that's the spherical coordinates. So triple integral in spherical coordinates. So first thing is the conversions. Okay, so this is x. Sorry, this is x. This is y. This is z. Right? And while doing conversions in the cylindrical or in the polar, remember that you have the r, d r, d theta. Right? Now we have rho squared and sine psi that we need to multiply. Okay, perhaps an example, and after one or two examples, I think we can finish. And at the end of the lectures, I would like to have some feedback sessions with you. Hope you don't mind to get uh, to play some games. Okay. So where do we apply this conversions for the sphere? Okay. The most obvious way, or the most obvious reason, is when you see a sphere formula. Then you can imagine that you could transform the equations into a sphere. Okay, let me give you some context on how to apply this formulations. Okay. evaluate this, where B is okay. When you see any formulations in the interval, that means you can apply the sphere conversions, and you can turn your formulations, your equation into a sphere formula. So first is you could see that we could have this formulation. So this is supposed to be its radius is 1, right? From 0 to 1. And because there's no additional information given, then we could just take the triple integral. Let me just write the question first. This equal 0 pi 0 2 pi. This is psi. This is psi. This is theta. This is rho. And this is 0 to 1. And the inside will be E with rho squared. So it's supposed to be rho squared, and then with power of 3 over 2. So it's supposed to be a cube. Oh, sorry. It's supposed to be rho cube. And this is rho squared. Rho squared sine psi, and then d rho d theta d psi. And then solve for each of this. We could take this separately. So we could take this 0 pi and sine psi d psi, 0 to pi d theta, and lastly we could take this rho squared e rho cube d rho. And we could take this as a substitutions if you would like to take this as a substitutions. Du is 3 rho squared d rho. This will be have 1 over 3 e over e with rho cube. And this part will be negative cos psi from 0 to pi. This will be 2 pi. And this will be 1 over 3 e rho cube from 0 to 1. So 4 over 3 pi, and then e minus 1. That's the answer. Okay. Another example. Maybe I'm just giving you questions here. Find the volume lies above cone Z equal and below sphere So first, perhaps, how to get the 0 to pi and 0 to 2 pi. Okay, this is from the restrictions on the sphere. Okay, at the beginning, I told you that the theta is a full circle from 0 to 2 pi, right? But for psi, it's supposed to be just this, right? From 0 to pi. Do you get what my point from here? The theta is full circle like that, right? The full one for psi is just this, okay? Because if you take this into back sides, it's it's going to be the other sides, and it's the same thing when you just rotate this through theta, right? Okay, do you get the logic to find to determine the restrictions? So it's supposed to be, the example is, because it doesn't have any requirement, so this will be a fully ball, just a ball, like usual ball. So it's just a sphere with the radius 1. The B, this B, okay, this B. Is that okay, Randall? Okay. Okay, the next question is this, but I think I will just describe this solutions later on Monday, and we can move to, or maybe having more exercise and giving you one or two more questions later on. And I will just finish up until here. Okay, so let's open some discussion. If you have any questions, do you have any question? Okay, if not, then let me stop this sharing, and we will discuss this example on Monday. Okay, so let's stop this sharing and me. Okay, if you haven't scanned the QR code, you can scan. Okay, and then we are going to play some game. Okay, so please get ready to prepare your smartphone. Or if you are in the smartphone now, you can go out and prepare your camera to scan the QR code. Okay, please join, and hopefully you guys can join all. Okay, I think we can start. Okay, anyone who wants to join? Just have 5 students joining. Okay, anyone? Okay, anyway, we could start now. Okay, get ready. And I hope the time is enough for you to check the answer. I hope 3 minutes is okay. I hope. Okay. One student submitted. Okay. Still have 1.5 minutes. Okay, 2 students submitted. Okay. Okay, 1 minute. 1 minute left. Okay. Okay, go to the next round. Okay. Okay, get to next one. Question 2. Find the volume of the solid. Now a little bit more time. More than 3 minutes. I hope enough. Okay, 1 minute 30 seconds. $45. 5 for a 3 students. Okay, good. Okay, I believe should be last question. Get ready. Okay. Yeah, you need to type in the answer. Okay, around 1 minute left. Okay. Oh, okay. I think it's too easy, right? Too easy. Okay, so that should be the last question. And who's the fastest one? Oh yeah. So yeah, congratulations, it's Rion, right? Yeah, congratulations, Rion. Yeah, winning the game. So I think we'll end up until here, and thank you for joining uh the quiz. Okay, and yeah, uh, probably around next week I will also preparing the quiz for chapter 14. So prepare your time and please look up into the Moodle. Okay. So thank you for joining, and I think see you again for Tuesday. For Monday. Okay, Monday class. Okay, so you can leave the meeting if you want. Okay, see you again.